Now we want to look at what happens when we try to do address translation in parallel with cache access. We start out with a virtual page number and a page offset. That's your virtual address format. Then the translation look-aside buffer translates the virtual page number to a physical page number, and the page offset is still the same after the address translation. For cache access purposes, this physical address is divided into tag, index, and offset fields. But don't confuse the block offset with the page offset. Notice in this example that the page offset is 12 bits, so the page size would be 2 to the 12th, or 4 kilobytes. How much physical memory, though, is there? Well, that's determined by the length of a physical address, which is 25 bits long, and therefore there must be 2 to the 25th bytes of physical memory in this example. Now that's horribly small by today's standards, but it serves for illustration. If we want the cache to be indexed before address translation completes, we need to have the index field be entirely contained within the page offset. So we kind of need a bigger page offset there. If the physical frame number overlaps the index, we don't know what the index is until address translation completes. But if the page offset is big enough for them not to overlap, then while we're looking up the page number in the TLB, we can be accessing the cache set where the block would have to be if it's cached. In that case, the cache hit time reduces from 2 cycles to 1, but there are some constraints. Suppose our cache is direct mapped. This means the index field is just the line number. So the line number concatenated with the block offset must fit inside the page offset. Now if I tell you the line number and the block offset, that completely determines where in the cache this field resides. So if we have the situation where the index field contains the line number because the cache is direct mapped, what's the largest that the cache can be? Think about it for a minute. Yes, 1 page, because the index can only refer to a single cache line. You see, if it's a set associative cache, then the index field just tells you the set, and the set contains more than 1 line, so the cache can be larger than a page. So thinking back to the last lecture, if we want to increase the size of the cache, we can make the cache set associative because that increases the tag width and decreases the width of the index. Remember that in the example we started out with, we had a direct mapped cache with a 7-bit line field in the last lecture, and then we went to a set associative cache, and those 7 bits were compressed into a 6-bit index field. So as the cache gets more associative, then the width of the index field diminishes, and when it becomes fully associative, the index field disappears altogether. So how can we use this information to allow cache access in parallel with address translation? Well, for new machines, we can select page size so that the page size is greater than the cache size divided by the associativity. But if the page size is fixed, we need to select associativity so that the associativity is greater than the cache size divided by the page size. Now that can be a pretty severe constraint. If we look back at 2 example architectures that I had lying around, both of which, by the way, are more than 30 years old, in the Motorola MC88-110, the page size was 4 kilobytes, and the I cache and D cache, that is, the instruction cache and data cache, are both 8 KB two-way set associative. The fact that they're two-way set associative means there's 4 kilobytes per way. And so if the page size is 4 kilobytes, we can do the cache access in parallel with the address translation. On the digital equipment VAX series, which was a really influential architecture of the late 1970s, the page size was only 512 bytes, which is the smallest page size I've ever seen. For a 16 KB cache then, we needed the associativity to be greater than 16 KB divided by 512 bytes. and that means 32-way set associative. Now, I don't think I've ever seen a 32-way set associative cache. I've seen some 16-way associative L2s on Sun machines of about 15 years ago, but 32 was really severe and just not feasible because it first increases the cost of the associativity hardware, and secondly, it makes the access time unacceptably long, not to mention that it really ramps up power consumption. So you'd never build a cache like that today. So I want to finish off with 3 alternatives for cache indexing and tagging. And this is contained in section 5.2.6 of the new textbook of the 2016 Solihin textbook. First question, what's the main disadvantage of a physically indexed and tagged cache? What is the organization that we've just been discussing in the last diagram? And what is the main disadvantage of virtually indexed and tagged? Well, the main disadvantage of physically indexed and tagged is that access time is too long because you need to complete the address translation before you can start to access the cache. And the organization that we've just been discussing in the last diagram is virtually indexed but physically tagged because we saw that the index gave us a virtual address, but we had to translate it to a physical address by the time we accessed the cache. What's the main disadvantage of virtually indexed and tagged? Well, it's that the cache can't be shared by multiple threads unless you have a way of moving a block within the cache when you get a new process's virtual address for existing data. So you got 2 processes, both of which are referring to the same addresses, but they use different, same physical addresses, but they use different virtual addresses for them. So then the cache lines need to move to a different place in the cache. Okay?